climate is changing. Global temperature is rising, about 1.1 degrees Celsius since 1880. The oceans have absorbed this heat, so they are also warming, with an increasing acidity of surface waters, which has increased by 30% since Industrial Revolution. The Arctic sea ice has declined rapidly its extent and thickness over the last several decades. As a consequence, sea level is rising, about 20 cm in the last century. Glaciers are retreating everywhere, the snow is melting earlier, and the number of extreme events, such as high temperature peaks and intense rainfall, is increasing. Climate has always slowly changed due to biotic processes, astrophysical variability, or volcanic activities. However, the scientific community compactly agrees the main cause of current global warming trend is anthropogenic. In fact, the human activity has increased the concentration of greenhouse gas. Why are greenhouse gases so important? The heat-trapping nature of carbon dioxide and other gases was demonstrated in the mid-19th century, so that there is no question that increased levels of greenhouse gases must cause the Earth to warm in response. And to give you an idea, carbon dioxide levels raised from 280 parts per million to 400 parts per million in the last 150 years. What's going to happen in the near future? To answer this question, we need climate models. The real world is a complex system. It is made by a large number of interactive components whose behavior is non-linear. A climate model consists in a set of equations which describe the interaction between the solar radiance, the atmosphere, oceans, land surface, and ice. The human activity is described by the representative concentration pathways. For greenhouse gas concentration possible futures, the optimistic curve assumes that greenhouse gas emissions peak now with the subsequent decline, while in the pessimistic case, emissions continue to rise throughout the 21st century. I'm handling output data from the Regional Climate Weather Research and Forecasting Model, a numerical weather prediction system which can generate atmospheric simulations. This model has a pessimistic attitude. It assumes the worst pathway, hopefully not the real one. The use of visual representation has always been, and is, an integral part of science, as it helps scientists to better understand complex phenomena. In fact, visualization plays a crucial role for sharing scientific results in an easy-to-understand manner. I focused on temperature variation, which is the most evident feature of climate change, writing some Python pipelines in order to extract all the information from NetCDF output data. The model forecasts the temperature evolution over the southern and central Europe from 2006 to 2099. And here we see an example of how the mean surface temperature changes in August. However, it is also important not to lose the third dimension. In fact, different altitudes carry different pieces of information. Global warming often occurs faster at higher altitudes, on mountains, for instance. And what happens on mountains has a deep impact on critical aspects of our economic and social system, such as access to water sources. If more than 1 billion people don't have daily access to clean water, climate change will definitely aggravate the situation, with also serious implications for agriculture. Global warming will amplify existing risks and create new risks for natural and human systems. Thanks to the collaboration between science and informatics, by building complex models and running supercomputers, we can foresee what is expecting us and our planet.